I like these examples because they relate the forces with the motions, and every time I see problems like those, I think of velocity graphs. All of them can be solved with the help of velocity graphs. Can we do them with equations? Yes, but we will spend a lot of time and we don't want to do so. So problem 12. An object accelerates from rest due to a constant force. That constant force is the only force, is the sigma F, right? So what should the force be so the object traveled a distance that is 4 times bigger in the same time? So by using a constant force F, the object does a displacement delta x. What should the force be so it does a distance 4 times bigger? Which means that we have a graph like this. So initially it speeds up from zero, right? From rest, starts from rest. It gets some velocity at some time. And we know that the displacement, meaning the area under the graph, is the displacement, right? And we know that, so this is the displacement, delta x, which is half the base times the height. Now, we want the object to speed up in a different way, starting from rest again, and we want at the same time to do a distance 4 times bigger, meaning it goes so fast that the area under the graph, now this area, will be 4 times bigger than this. So this area, delta x capital, let's say, is half base, which is the same, times the height. We do understand that everything is the same besides the height. And just because we want this to be 4 times bigger than that means that the height should be 4 times bigger than this height. So, but this height is the final velocity the object gets, so this height will be the new final velocity. So the new final velocity should be 4 times bigger. That means that the slope of this, which is rise over run, is 4 times bigger than the acceleration of this one, which is this rise over the same run. So just because the rise is 4 times bigger than this rise, the slope, the acceleration is 4 times bigger. And for an acceleration that is 4 times bigger, we need a force that is 4 times bigger. Problem 13. Again, I need to use the velocity time graph. I have an object, a car, that has an initial velocity. It stops at some time t because of a constant force. What should the force be so the object stops in double time, so it slows down more smoothly? We have this case. So we have two cars. They both slow down from the same initial velocity. They stop. But the one does it at time t, the other one does it at double time. What do you think the acceleration, what do you think the slopes are? So the slope of this is rise over run, while the acceleration of this is, let's call it 2, is rise over run. So we see that in this case the slope will be exactly the half, right? For us to slow down in the double time, we will use the half deceleration, meaning the force needs to be the half. Problem 14 talks about accelerating from rest with a constant force, and in some time t we do a distance delta x. Now, what kind of force should we have so we travel the same distance at the half time? Okay, so in the first case we have something, a car, an object that accelerates from rest, and in some time it does some distance delta x. Now, it will have some kind of acceleration, some kind of a slope because of a certain force. Now we want it to do the same displacement, the same distance at the half time. So we want a triangle actually that has the half base, but it needs to have the same area. So what kind of triangle should we have that will have the half base but the same area? So this area is half base times height. This area, which will be the same, should be half its own base, T1 over 2. I hope you can see the orange. Yeah, that's not good. Let's try blue. Blue. And we need to know the height. There will be some velocity v, which we don't know yet. All right? So these two areas, the blue and the orange, should be the same. These two should be the same. So if I make these two equal, so half T1 V1 should be half T1 over 2 V, the unknown. So this goes, T1 goes, and I find that V1 will be, all right, this goes with this, time T1, T1, so this is left here, this is left here, this is left here. Or else if I solve for the velocity, this velocity should be exactly double. So this should be exactly double than that, okay? If we have the half base, we need to have the double height, so we have the same area. Double height, all right? Let's go back to the acceleration. So what kind of acceleration do I have here? And what kind of acceleration I have here? Let's use black. So in this case, the slope, the acceleration, is the slope, which is rise, right? Rise over run. So the rise goes from 0 to V1, it's V1, and the run is T1. Let's see the slope here. What do you think the slope is? Let's see. What's the new slope here? So the new slope, let's call it 2, will be this rise, which is 2V1, over this run, which is the half time. And this produces a 4V1 over T1. This slope is 4 times bigger. The acceleration that we need in this case is 4 times bigger, and the force is 4 times bigger.